Welcome back for Math 205, and today we shall study chapter 5, and it's the Laplace transformation. Okay, here in this section we shall give the definition of the Laplace transformation, which is 5.1. Okay, the definition, we have a function f of t. Here we keep our variable t and define for t greater or equal to 0, from 0 to infinity means. The Laplace transform, okay, we denote for it by L, is defined by L of f of t. It's a function of s. This is a function of s. So you need to evaluate this integral. This is the improper integral, and you put f of t inside it and you evaluate this integral. And as we know from calculus, we can use limit also. So I put it in terms of limit, and you need this convergent to be convergent integral for that. So this is the definition of the Laplace transform. Okay. Notation, usually we use L or capital F of s for the Laplace transform of this, and I put it here. The domain is the values of s, because this is a function of s, such that this integral in the right hand side converges. So this is the domain, is all values of s such that this integral number 1 is converged. So we are interested in this integral number 1 to be converged. Of course, in this course, we shall not do some integrals. We shall have a table for calculating Laplace, and I will give it later on. So we concentrate in this function, and we put it here in this integral, as I said, and it is defined to be like the convergent integral of this for some values of s. Okay, let's go for the proper. Before we go for some examples, I will give you some theorem, very easy. L is linear operator, and we know what's linear, and we studied it before when we have linear operator for the differential equation. So this is the properties of the linearity, number I and number I2. So here L of f plus g equal LF plus LG. And if you take constant multiply by f, still you can get the constant outside, and it will be where c is a constant. Now I'll give you some examples for that. So let's take f of t here equal to 1 for the first example. F of t, this is your f here, f of t equal to 1, okay? So I put it here. This is the definition of the Laplace, okay? And now I put f of t equal to 1. So L of 1 is just the limit. As we said, we replace this f by 1 here. So I don't put it, it's very clear, it's 1 here. So integration of this, and I use the limit. If you go back here, I use this definition with the limit here. So you need the limit and integration. This is integration with respect to t, so you treat s as a constant. So this is the integration, and then you evaluate this limit. And of course, when you put t equal to h and t equal to 0, so you get this here, and this is the limit. Of course, this limit, we know, since s positive here, we take s greater than 0, this limit tends to 0 as h tends to infinity, because like e minus 2x or 3x, like that when we have it in calculus. So the final result of this limit is just 1 over s. And the domain will be s greater than 0, because this is convergent integral, as I said, for s greater than 0. So this is very clear, and for the constant function. Now the second example, I take it f of t equal exponential at. So here f of t equal to 1, and here I take more general little bit, exponential e to the power. If you put a equal to 0, this is 1, the same as example 1. So we evaluate again, we use this the above one here, and again we put instead f equal to exponential. So you put it here, you see. So I put it and it's like that. I take as a minus as a factor and I just add these powers here. And now this is again like what we treat before when you have exponential. So this is again the result will be 1 over s minus a without evaluating the integral. As we get here, you see here in this one, we get 1 over s. So here what we expect, we get 1 over s minus a. So this is the result and this is your domain here. So this is the second example for that. So this is the way how to do it. Just we put these functions and the integrals and we evaluate these improper integral. Of course, we shall not deal with these things as I said. We shall have a table. I just want to show you how we do it. Now let's go. This is the table which is very important. This is, I said, we have the following table for Laplace. This is your function f of t, and this is your L. This is the L of f, and this is your domain. I put it just to inform. So this is what we did here. When we get 1 over s, and this is our domain here. So this is what we did, and we did also this one in the example 2, and we get 1 over s minus a. Okay, t to the power n, if you do it, you will get n factorial. This is n factorial over s to the power n plus 1. And if you carry on, so we mix, then t to the power n exponential, we get number 4, and this is it, see? And this is more general than if you see number 2, because number 2 is a special case of number 4. If you put a equal to 0 here, okay, you get number 2. Okay, so if you put a equal to 0, you have. So this is more general, and you see it here, the difference in this. You have s minus a coming to the power n plus 1. Okay, so this is the table, and now we go for cosine, which is very important. Cosine and sine, it will be s over s square plus b square, and the domain will be s greater than 0. If you go for sine, see the difference between sine and cosine. Here you have s for the cosine. Here for the sine you have just the b constant, and it will be the root of this. And then it's mixed with exponential with sine and exponential with sine. Cosine exponential will get more general than this one, as I said. It will be s minus a. And here you have s minus a instead of s, and it will be like that, and you have the domain. And for the sine, you get s minus a, and here be the same as the cosine sine. It's a little bit only just in the s minus a. So this is the more general. Well, the last two ones, the cosine, hyperbolic, and sine, it's not too much we are using it. I put it here in the table. So we concentrate on all these 7 here. So this is the table. We shall use it now. I will give you an examples how we shall use this table. It's very easy, and if you are doing in September the exam, this table we shall give it to you with some properties also. So you don't need to memorize this, just use the table as I said. Okay, now I give you an examples, very easy example to apply the table direct. I have 3 functions here in this example, 3 plus 2 t cubed plus 4 e2t. So I apply the linearity. I take the L over this, and the constant outside. Okay, so L of 1, L of t cubed, L of e2t. So the constant goes out, not the variable, the constant. So property number 2 of the linearity of L itself. Now L of 1, we go for L of 1 from the table. If you go page 74 again, L of 1, this is the one here, it will be 1 over s. So I put instead of L of 1 over x, I multiply by 3, I get this term. Now L of t cubed will be n factorial from the table over L of t cube n factorial over s to the power n plus 1. So it will be n factorial will be 3 factorial because n be 3, because n equal 3, and divide by s to the power 4. And this 2 outside. And the same for exponential. Here a equal 2, it will be 1 over s minus a, and it will give you this one. Now I just multiply here, 2 multiplied by 6, 12, and 4, I write it like that. We don't need to do more than that. We leave it like this way. We don't need to put it together. So what's the domain? If you see the domain, how you guess the domain? Domain is this is true for s greater than 0. This is true for s greater than 0. This is true for s greater 2. So it's cover all these cases. You need to take one domain which is s greater than 2. So this is an example 1. In example 2, I take the number 6, I think there, if we go for it. If we go there, I take exponential, cosine, exponential, sine. Okay? So if you do it again, you take the 3 outside as linearity, and then you go for the table. Here a equal 2, so s minus 2 square. Here b 4, so you square this, 16, and s minus 2 up. This is for the cosine. But for the sine, you take the square of 16 here, it will be 4, you put it, and s minus 2. And as I see, this is s greater than 2, so this is the result will be for the example. Okay, now let's go for properties of the Laplace transform, which is 5.2. In fact, in this chapter, the 5.1, 5.2, and 5.3, we go very quickly for it because it's a background for section 5.4, which we shall solve Laplace transform by using the table. So here, the properties of Laplace, I just give it, which is not too much important because we have the second property, which is very important. This is called shift property, number 1. Okay, I list them. If L of f of t is just f of s, this is the Laplace transform for function. And then you can evaluate this. Well, this is already, we have it in the table. This is just another way to evaluate L of exponential f, and it will be like that. I gave you an example here, and then you can see it when you go back and read these notes. This is, we can do it by the table direct, or you can do it by this property here. Okay, so I just want to show you how you evaluate. So here it's very easy. Your f of t is cosine 40, and your alpha equal to, so in fact L of f of t is just this one here. So this is your f of s. So just you need f of s minus alpha. So exponential this, just you put here s minus alpha, alpha equal to, so you get it. So either you get it from this property or from the table. So this is very easy example for this property. And if we go for, this is the most important now for the second and the third, which is more general. Property, Laplace transform for the derivative of a function. So it will be L of f of t of s minus f of naught. Okay? And if you go for more general derivative, nth derivative, you get Sn Lf, Sn minus 1, f naught, and you carry on until you finish with this one. Okay, I put special cases because I know this is very important when we solve differential equation. Because if you remember in the differential equation we have y prime, so here y prime, here y double prime, then coming, and let's go until we go for the higher derivative. Okay, now this is special cases. N equal to 1, we get number 2. We get number, it will be number 2. I put it here, okay? Number 2, when you put n equal to 1 here, just SLF minus f of naught. Minus f of naught. So 2 term, you get number 2. I put it here. Okay, n equal to, what we shall get? N equal to, so second derivative, it will be n equal to s square LF, then you put n equal to here, minus s of naught, then you stop for 3 terms only, it will be minus, there's minus f prime of naught, because n of 2 here. So this is the case n equal 2. And then n equal to 3, you carry on. And you put again n equal 3 here. And so s cube LF minus s square f of naught minus s f prime of naught. Then you stop when n, it will be the fourth term here. It will be f double prime of naught. So n equal 3. And if you carry on, you can carry on until you want to stop. This is for n equal 4. And it will be S4 and the property number 3 if you put LF, then minus S3 f of naught, then minus S square f prime of naught, then minus S f double prime until you stop for that one. So this is the most important. You don't need to memorize it. This is, we shall give it to you on the table if you are having exam in September. The last property, I just put it here just to the derivative instead. Now derivative of Laplace, I want to tell you about, there is another property about it. This is the same as the shift property, but for the derivative here you need to take, so L of f of t is equal, then L of t and f of t is just the derivative. You see the derivative of Laplace here, because f of s is the Laplace. So this is just, we'll finish that about the properties of the. Okay, now if we carry on, as I said, this is just the background. I'm going very quickly to this. We shall study the inverse of Laplace. This is 5.3. Now, if L of t, this is what we have, then we can we can find f of t now. If I gave you f of s, you can find f of t the other way around. So your f of t is called the inverse of f of s. And again, the same theorem, we have theorem for L, we have theorem for L inverse is linear again. You see, the same as we have it for the L itself. So these two properties, I and I2, we know it, as I said. Now I will give you some example for calculating the inverse. Okay, L inverse, this is very easy trick. L inverse of 3 over s. So I gave you the second now column of the table, and we need the first column of the table. So you take 3 out, and you go here in the second column. What's L inverse of 1 over s? It's 1. 1, it will be 1, multiplied by 3, so we get the result 3. And if you carry on like that, you see, if I go to the table, I am just want to show you what we are doing. You see, I am giving you the second column of the table here, and I want the first column of the table itself. Okay, so this is what happened in the inverse, in fact. So this is what we did. Now here I gave you the function of f of s, and here of s, and I want to find the inverse. So this is, in fact, this is the sine, but here we need, here the square, this is 5, so here must be square root of 5 up. So I multiply by square root of 5, and I divide by square root of 5 to make it in the form, standard form of the table. So, and I take 9 is outside, so it is in the standard form now. And here, if you see, this is L of Tn. So here you need 5 factorial up. So I multiply by 5 factorial, and I divide by 5 factorial to put it in the standard form. So you need to do this. You multiply and you divide to make no difference. So then you can apply the table for this. It will give you sine square root of 5t. And this one will give you t to the power 5. This one, if you go to the table, is t to the power 5 over 1. So this is, we'll finish that example. Now, there is a form how you calculate L inverse of the ratio P over Q. And the degree of P less than the degree of Q of the polynomial. So we have 3 cases. when it's called non-repeated linear factors, means that q you can factorize it linearly and non-repeated. So from calculus, as you know, for integration for partial fraction, we do the same exactly. So p over q, we write it. If you do in calculus integration, you remember these forms. So a1 over s minus alpha, a2 over s until an. And we need to calculate, in fact, these a's. Okay? So this is the result. How then you take L inverse for both sides, and you get it. And this is, if you remember, you go to the table and you calculate. This is s. It will be e alpha 1 t and until this. Repeated linear factors, this case, second case, when you have, this is linear and repeated. So you do it in this way, as in the calculus, and you take, it's not difficult, you do it again, and you take the L inverse again here for P over a Q. So this is the case 1, and this is case 2. Case 1 is linear factor non-repeated. Case 2, linear factor repeated. So you do it. So what's the missing here? The missing is a1, a2 until an, and then you use the table. The last one, which is irreducible quadratic form. Quadratic form for a q. We are discussing the q. So a q can be written in this form. This is a little more complicated, but it's not too much coming. So you need to calculate, in fact, gamma 1, delta 1, delta 2. The missing is all these, see, until. So this is the general form, in fact, and I will leave it for you. You can see it in the notes later on, or in the book you can find some example, and it will be very clear there. But we must be careful if you have quadratic a little bit, because sometimes no missing term in the s. Now we go for I will give an examples for how you calculate the inverse. This is an example I gave here. Cover, in fact, case 1 and case 3. Okay? So I want to calculate, this is P over Q. Okay? So this is P over Q here. I put A over S minus 1 as in calculus. And here, because there is no S, so I put PS over S squared plus 4. So I need to calculate A and B and C. And you know this from calculus, we do these things. And I calculate for you A and B and C. It's very easy. And we shall see it this when we do 5.4. I will show you how we solve this differential equation using Laplace by using the table. And we shall do many times inverse for calculating the inverse of this function of S. So what's happened now? Okay, this is what happened. Really, we find A and B and C, and this is A and this is B and C. They are equal, so we put them here. Okay, and this one here, all A and B and C here. Okay, and then we take L inverse as for that one. So we have that one. So A, take A outside, because A is, as you said, L inverse is linear. So we take A outside. I put it direct. This is your A here. 1 over S minus 1. And then I separate this to two terms, one with S and one without S. So I put it in this two term, you see. So I take the B outside, 3 over 5. And I put the C also again outside. If you see something in red here, because here, straightforward for, this is the cosine. Okay? But here in the last term, it's not straightforward for the sine. You need to take the square root of 4. So I multiply by 2 up, the square root of 4. I multiply by 2 and divide by 2. So now it will be in the form of sine. So it will be this one from the table. So e to the power t. If you go for the third rule in the table, exponential. And this is for the cosine. cosine bt, b equal 2 will be, b square will be 4 here. And this is for the sine bt, b equal 2 as I said. And it will be 3/10 because we multiply by 2 to put it in the standard form. This is will finish the inverse, and we finish 5.1 and 5.2 and 5.3 very quickly, but it's not just as a background. The most important is how to solve a differential equation by using Laplace transform and using the table of the